Okay, today, let's finish these two sections. And then we turn to study section 3.1. Section 3.1 is about a determinant of a square matrix. Topic 1, first. Associate with a matrix, there are two subspaces. Here is the definition. Yeah, definition. Let A be a general M by N matrix. There are two subspaces associated with this matrix A. Number one, let me cut the matrix into columns. Let A, the first column is A1, second column A2. The last column, because I assume the matrix A, the size is M by N, so N columns, AN. Each column is a vector. Now I let H be the set spanned by the columns. H is a subspace because each column has how many entries? Each column has A has M rows, so each column has M entries, has M entries. So each column is a vector. So each column, right, AI, is a vector of M entries. So each column is in ROM. Span is linear combinations. So linear combination of vectors in ROM, still in ROM. Therefore, H actually is a set in ROM. We call this subspace of ROM the column space of matrix A. Yeah, H is a subspace of ROM. We call H the column space of matrix A. The notation is denoted by this notation, COL of A. COL of A. Okay, this is the first subspace associated with a matrix. Now the second subspace is called null space, B. Let H be the set of all the solutions of this linear system. The right side is 0. So this linear system is a homogeneous linear system. Yeah. Solve this linear system and put all the solutions together. We have a set. That set is called the null space of matrix A. Take a look at the size of each quantity in this equation. Matrix A, the size is m by n. X, the solution, the size is n by 1. The right side, m by 1. So solution of this linear system is a vector in Rn, not in Rn. Okay, so each solution is a vector in Rn. H is the set of all the solutions together. So H is a set in Rn. This time, H is a subspace of Rn, not of Rn. And we call this H the null space of matrix A. And the notation is denoted by this notation, NUL of A, NUL of A. Associated with any matrix, there are two subspaces. One is column space. Column space spanned by the columns of matrix A. And null space. Null space is the set of solutions of this homogeneous linear system. So definition is important. Okay, now take a look at some examples about this definition. Example 1. Can you construct a 3x3 non-zero matrix A? Non-zero matrix. When the matrix has one entry non-zero, then the matrix is non-zero matrix. And a non-zero vector B, when the vector has one non-zero entry, then the vector is non-zero vector, such that a B is in the null space of matrix A. B is in the null space of matrix A. That means that B is a solution of this linear system. In other words, that means that A times B is 0. Yeah, B is in the null space of matrix A, means A times B is 0. Is 0. Now, can you construct A and B so that A times B is 0? There are many solutions. Let me construct matrix such a matrix A and the vector B as simple as possible. Okay, A is 3x3, non-zero. Let me try this matrix. Non-zero. Whenever one entry is non-zero, the matrix is non-zero. So let me try this matrix. 1, 0, 0, 0, 0, 0, 0, 0, 0. Yeah, this is a 3x3 non-zero matrix. Now let me pick a non-zero vector so that A times the vector is 0. Also, I try a vector as simple as possible. Let me try. A times B should be 0. Okay, let me put the first entry 0, second entry 1, the third entry 0. Then easy to see that this matrix A times this vector B is a 0 vector. So B is in the null space of matrix A. Done. Okay. First example. Now, second example. Example 2. Can you find a basis? A basis is a spanning set. A smallest spanning set is called a basis. Find a basis for the null space of the following matrix. The following matrix. The matrix is let me see. It is a 3x5 matrix. First row, second row. Third row, 3x5 matrix. All right. How to answer this question? Find a basis for the null space of this matrix. Recall that a null space is the set of all the solutions of this linear system. That is the definition. Now, to answer this question, we need to solve this linear system to find all its solutions. To answer the question, solve this linear system. How to solve the linear system? Augmented matrix. Augmented matrix. Augmented matrix. Coefficient matrix. Together with the right side. Right side is 0. Coefficient matrix, let me copy coefficient matrix. Right hand side, 0, 0, 0. Now, to solve this linear system, reduce the augmented matrix to epsilon form by forward elimination. Then further reduce the epsilon form to reduce epsilon form by backward elimination. Okay, now let me skip the details. Okay, this matrix is equivalent to the following reduced epsilon form. 1, -2, 3, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. Separate. Yeah. This matrix, the final matrix, is in reduced epsilon form. We cannot introduce to this matrix any more zeros. After we reduce the augmented matrix to reduce epsilon form, then write the final augmented matrix in equations. The final matrix in equations is the following linear system. In equations, the final matrix is x1 minus 2x2, x4, x5, 0. And the second row is this equation. Two x3 is 0. The last equation, the last row is the equation 0 is equal to 0. Yeah. 0 is 0. Yeah. Okay. We have 5 unknowns: x1, x2, x3, x4, and x5. Which ones are basic unknowns? Let me see. Basic unknowns. First column contains a pivot number, so x1 is basic. Third column contains a pivot number, so x3 is basic. x2, x4, x5 are free variables. Now I solve this linear system for the basic variable in terms of the free variables. Solve the linear system for the basic variables x1 and x3 in terms of the free variables x2, x4, x5 to get all the solutions of the linear system, all the solutions to get the general solution. General solution. Okay. From the first equation, keep the basic variable on the left side and move all the terms to the right side. From the second equation, keep the basic variable x3 on the left side, move all the terms to the right side. Plus 2x3. Where x2, x4, x5, free variables, we can arbitrarily assign values to x2, x4, and x5. Yeah, these are all the solutions of this linear system. Null space of matrix A is the set of all the solutions of these linear systems. Now, next step, okay, write the solution in vectors. In vectors, some questions. Should it be 2 by 3 instead of 2 by 3?
I think just in the second equation, it just needs to be 2x5 instead of 2x3.
The second equation, you mean this equation?
Yeah, sorry. So like the negative 2x3 should be negative 2x5.
Oh, correct. Sorry. Here. Yeah, this is a 2x5. Here, sorry. 2x5. Thank you. Thank you. Okay. Okay. Now, general solution. Write general solution in vectors. In vectors. Okay. Vector x. Vector x is the vector of the unknowns, the 5 unknowns. x1, x2, x3, x4, and x5. Now plug in these two equations in x1 and x3. Then I get 2x2 plus x4, 3x5. X2, keep x2, okay. Then x3 is negative 2x4 plus 2x5. Then keep x4, keep x5. Split this vector into a sum, In the sum of vectors, the first vector is for x2. So 2x2. Second entry is x2. The third entry, low x2. So I put 0. The fourth entry, low x2, 0, 0. Then plus second vector. Second vector is for x4. X4. Here, the second entry here has low x4, so put 0. The third entry here has x4, negative 2x4. The fourth entry has x4, so x4. The fifth entry, low x4, so put 0. And then plus the third vector. The third vector is for x5. First entry has x5, so put negative 3x5 here. Second entry, low x5, 0. Third entry, there is a x5, 2x5. The fourth entry, low x5, so put 0. And then last entry, x5. Okay, now next, let me take out x2, x4, and x5. Okay, let me write solution here. Here. It's equal to take out x2. So x2 times 2, 1, 0, 0, 0. Plus take out x4. 1, 0, negative 2. 1, 0. And then plus take out x5. Negative 3, 0, 2, 0, 1. Here, x2, x4, x5, arbitrary. So each solution of this linear system, each solution is a linear combination of these 3 constant vectors. Let me name these 3 vectors. Say, how about let me name this U, V, W, for example. So U, V, W actually span all the solutions. Therefore, conclusion is, therefore, null space of the matrix A, null space by definition, okay, always definition. Yeah, another question coming. X3 is negative 2, yeah, correct, yes, yeah, X3, yeah, okay. Null space by definition, always keep the definition in your mind. Null space means the set of all the solutions of this linear system. Now, all the solutions spanned by U, V, and W, these three vectors. Spanned by U, V, W, these three vectors. And it is easy to see that these three vectors cannot be spanned by each other. They are linearly independent. How to see these three vectors are linearly independent? Solve this equation. Alpha 1, U, alpha 2, V, alpha 3, W is 0. Solve this vector equation. You will see the only solution is 0, 0, 0. When this vector equation has only 0, 0, 0 as solution, the three vectors are linearly independent to each other. So because U, V, W are linearly independent, so this spanning set is a smallest spanning set. Therefore, it is a basis. Conclusion. A basis of the null space is the set of these three vectors. Yeah, U, V, W means these three vectors. Yeah, done. Yeah. Find a basis for the null space of this matrix. The answer is the set of these three vectors. These three vectors span the null space. And you cannot draw any of these three vectors from the spanning set. The smallest spanning set. Okay. Example number 2. Because the basis has three vectors, 1, 2, 3. Recall that the number of vectors in a basis is called the dimension of the space. So therefore, the dimension of this null space is equal to 3. Yeah. This space, it is a subspace of R5, because each solution has 5 entries. So each solution is a vector in R5. This is a subspace of R5. The dimension is 3. It is a 3-dimensional subspace in R5. And also from this example, we can see that the number 3, actually is the number of free variables. This is the number of free variables, or in other words, the number of free columns of matrix A. From this example, we see that dimension of null space is equal to the number of free columns. This is true in general. We have the following theorem. Theorem number one, you can find this theorem in the book. Theorem number one. For any matrix, any m by n matrix, we always have the dimension of the null space of matrix A is equal to the number of free columns. Free columns in matrix A. Always true. Always true. This is about null space. How about column space? How about column space? We have a theorem for column space. To find a basis for column space. What is a column space? Go back to the definition. Column space is the set spanned by the columns of the matrix A. To find a basis for column space, we need the following theorem. You can also find this theorem in the book. This is theorem number one. Number two, it turns out that the pivot columns of a matrix A form a basis for the column space of matrix A. How to use this theorem? Let me take this matrix as one example. Let me take this matrix as an example. Example number three. Example number three is about theorem number two. And then matrix A be the matrix in the previous example. And let me denote the columns. The first column, let me use this notation. Denote it. It is a vector of 3 entries. So this vector is in arrow 3. Second column, I use A2, A3, A4, and A5. Okay. Therefore, then column space of matrix A is the set spanned by the columns A1, A2, A3, A4, A5. So the columns is a spanning set, but this spanning set may be too large. I want to find a basis. A basis means I want to find a smallest spanning set. So how to drop vectors from this spanning set? Use this theorem. This theorem says that pivot columns form a smallest spanning set. We have 5 columns. How to know which column is a basic column, is a pivot column? How to know? The only way to know a column is a pivot column is to reduce the matrix to epsilon form. Okay, now let me reduce matrix A to epsilon form to determine pivot columns. After I reduce A to epsilon form, I still need to write down the matrix. One, negative 2. I want to determine which column is a pivot column. So I reduce it to epsilon form. I use the reduced epsilon form in the previous example. Okay, now from the epsilon form, first column contains a pivot. So first column in the original matrix, this column, pivot column. The third column has a pivot number. So the third column in the original matrix is a pivot column. So therefore, column space of matrix A, yes, spanned by all the columns, A1, A2, A3, A4, A5. First column, pivot. Third column, pivot. The other columns turn out to be spanned by the first column and the third column. So by theorem, this theorem number 2. Okay. I can drop A2, A4, A5 from this spanning set because A2, A4, A5 by theorem number 2, they can span by A1 and A3. Span means they can be written as linear combinations of A1 and A3. So drop, then I get this. Yeah, theorem number 2 says that these 2 vectors can span this space. By theorem number 2, a basis for the column space of this matrix A is A1. Please note that A1, I mean the first column of the original matrix, not the first column of this reduced epsilon form, okay? A3, yeah, done. Hey, column space in this example, because A1, A3 has only 3 entries. So this guy is a subspace of R3. The dimension is just 2. Yeah, dimension of this column space is 2. If you plot the graph of the column space, it is a plane, 2-dimensional, a plane in R3. The graph is a plane in R3, 2-dimensional. 2 actually is equal to number of pivot columns of matrix A. So dimension of column space of a matrix is equal to the number of pivot columns of matrix A. Yeah, this is true in general. It is the following theorem. Theorem number 3. Theorem number 3. For any matrix A, dimension of column space, the set spanned by the columns, is equal to number of pivot columns in A. Yeah. Now, this is a theorem number 3. Go back to theorem number 1. Theorem number 1, dimension of row space is number of 3 columns. A matrix, the number of 3 columns plus the number of pivot columns is equal to the total number of columns, right? Do you agree? Okay, so combining theorem number 1 and theorem number 3, we have the following theorem. Let me call this a theorem number 4. For any m by n matrix A, we always have the following conclusion. We have dimension of row space of matrix A. This is the number of 3 columns plus dimension of column space of matrix A. This is the number of pivot columns is equal to total number of columns. The number of all the columns. All the columns is n. This is equal to n. Yeah. About this topic. This topic is about section 2.8 and 2.9. 4 theorems. Next, let me show you one more example. Then I'm done with these 2 sections and we turn to study determinants of matrices. One more example. With this example, I finish these 2 sections. Example number 1. Example number this is number 3. Example number 4. One more question. Oh, yeah, question number 4. Example number 4. Thank you. Example number 4. Example number 4. Okay. We have 4 vectors. Let V1 4, 6, 3. It is a vector in R3. V2 5, 5, 4. V3 9, 1, 8. V4 yeah, 4 vectors. Now I let these 4 vectors span a set. Okay. Okay, let H be the set spanned by these 4 vectors. Now the question is, find a basis smallest spanning set for H. Okay, this is the question. Yeah. V1, V2, V3, V4 may be some of the vectors depend on the other vectors. We can drop those vectors depend on the other vectors from the spanning set. Okay. Okay. Now, how to answer this question? How to answer this question? Yeah. Which, yeah, this spanning set has too many vectors. I want to drop some. Which vectors we should drop? Which vectors we should keep? How to answer this question? Now I want to use theorem 2 to answer the questions. Yeah, theorem 2. Pivot columns of a matrix form a basis. Okay. I want to use theorem 2. Now I form a matrix from these 4 vectors. Matrix A. First column, I put V1 as the first column, V2 second column, V3 third column, V4. So I have a matrix. Then H spanned by these 4 vectors, now spanned by the columns of this matrix A. So therefore, H is column space of this matrix A. Yeah. Column space means the set spanned by the columns. Now H is column space. I can use theorem number 2. Theorem number 2 says that pivot columns is a basis. Now let me determine which column in matrix A is a pivot column. To answer this question, reduce A to epsilon form. Okay. Okay. Now, in detail, what is matrix A? Matrix A is first column is V1. Second column, third column, the fourth column. Perform elimination. I get epsilon form. 1, 2, 6, -5. 0, 0, 0, 0. Okay, now from the epsilon form, now I can see first column contains a pivot. So this column, pivot column. Second column contains a pivot. Second column, pivot column. Third column and fourth column are free columns. Therefore, by theorem 2, I can drop V3, drop V4 from this spanning list. So here I can drop V3, V4 and keep V1, V2, span V1, V2. Yeah. Therefore, conclusion. A basis for H, yeah, this H is the set of V1, V2. Yeah. Therefore, because this basis has only two elements, so therefore dimension of this H is equal to 2. Yeah, H is a subspace in R3. If you plot the graph of H, you will see a plane, right? Two vectors span a plane through the origin. The graph is a plane through the origin and in R3. Yeah. So done. The answer. Find a basis for this H. The basis is this. Done. Finish. Yeah. Okay. With this example, I finish section 2.8 and 2.9. Yeah, I'm done with this topic. Now we turn to section 3.1. Section 3.1 is about determinants. Okay. What is a determinant? Let me write this down. Topic 2. Topic 2. What is a determinant? The determinant of a square matrix. Yeah, square matrix. The matrix, the number of the rows and the number of the columns are equal. A square matrix A is a number. It's a number. This number is computed from the entries of matrix A. Why we call this number the determinant? This number determines whether the matrix A is invertible, whether the matrix A has inverse. Yeah, this number is called the determinant of this matrix A because it determines whether A is invertible. When determinant is a non-zero number, matrix A is invertible. When the determinant is 0, matrix A has no inverse. Okay, has no inverse. Okay. Second topic is about notations. Before I introduce you formulas to compute a determinant, I introduce you some notations first. Okay, notations. Yeah, notations. Okay. Number one, the determinant of A is a square matrix. For rectangular matrix, we don't consider determinant, no determinant for rectangular matrices. The determinant of a square matrix A, the notation is denoted by det of A. One notation. Second notation is this. Vertical line A, vertical line. Hey, pay attention. This pair of vertical lines doesn't mean absolute value. No, not absolute value, but mean determinant. Okay. All right, first notation. Second notation. I use Aij, this notation, to mean the submatrix of matrix A. The submatrix formed by deleting the ith row and the jth column of matrix A. Say for example, yeah, we have a matrix, 1, a square matrix, 0, 4, -2, 0, a square matrix. Okay, then say for example, what is A32? A32 is a submatrix part of this matrix, submatrix. A32, how to get A32? By definition here. Delete the third row and the second column of the original matrix. Yeah, let me delete the third row. Delete the second column. So A32 is this matrix. The remaining entries are 1, 5, 0, 2, 4, -1, 0, no 4. 4 has been dropped. Yeah, this 3x3 matrix is A32. Yeah. So Aij is the submatrix of matrix A by crossing up the ith row and the jth column. Okay. 1, 2, notation 1, notation 2. Now notation number 3. Number 3. I let C here. C is the first letter of this word called factor. Okay. Yeah. I let Cij below the following number. -1 to I plus j. The power is I plus j times determinant. Determinant is a number of matrix Aij. Yeah, Aij from here. Aij. Yeah. I let Cij below this number. Yeah, and give a name to Cij. We call Cij. Give a name. The Ij cofactor of matrix A, original matrix. Yeah. Just a name. Okay, just a name. Yeah. Call this number Ij cofactor of matrix A. Okay. This is a second topic. I think I am with these notations. I am ready to introduce you formulas to compute a determinant. Okay. Yeah. This is second topic. Yeah. Notations. I'm done. Now, formulas to compute a determinant. Okay. Topic 3. Topic number 3. Okay. The first formula. The first formula. Okay. A. If matrix A is 1 by 1 matrix, that means that a matrix has a single entry. Okay. I say matrix A is a single entry, a matrix of a single entry. Yeah. Then determinant of this matrix A is equal to this entry, equal to A. When A is 1 by 1, determinant is the entry. Okay, now B. For a general square matrix, for a general n by n matrix, let me write this matrix in detail. First entry, A11, A12, A13, and so on. A1n. Second row, A21, A22, 23, 2n, and so on. The last row, AN1, AN2, AN3, ANN. Yeah, n by n square matrix. Then the formula to compute the determinant of this matrix is the determinant, the formula of A is consider look at the first row. First row. Determinant is equal to A11 times C11. What C11 is? Yeah, C11 is here. Defined here. Yeah, it is a number. Plus A12 times C12 plus A13, C13, and so on. The last entry, A1n. C1n. That's it. Formula, very easy to remember. Entry times cofactor, and then make a sum. Okay. Yeah, This okay, yeah. How to use this formula? How to use this formula? Let me show you examples. How to use this formula? Okay, take a look at examples. Example 1. Under this topic, let A be this 1 by 1 matrix. The entry is negative 1.3. Then determinant of this matrix is formula is here. When A is 1 by 1, determinant is the entry. So determinant is negative 1.3. Done. Done. Example 2. Let A be a 2 by 2 matrix. Say A11, A12, A21, A22. Now the question is find determinant of this matrix. Solution. Okay. We have a formula. The formula is here. Formula is here. Okay. By formula, determinant of this matrix A is, look at the first row. A11, C11 plus A12, C12. What is C11? Go back to the notation. Yeah, notation is here. C11 is equal to negative 1 to 1 plus 1 times determinant of A11. So this is a negative 1 plus 1 determinant of A11 plus A12 times C12. C12 is negative 1 plus 2 determinant A12. All right, now let me simplify this expression. Negative 1 to 2, 1 plus 1 is 2. Negative 1 to 2, positive 1. So this is A11 determinant A11. Negative 1 to the third, 1 plus 2 is 3. Negative 1 to the third is negative 1. So minus A12 determinant A12. Okay, now let me determine A11, A12. Go back to its meaning. Okay, what they mean? Aij means the submatrix obtained by deleting row I and column J. Okay, now here. Okay, delete A11, delete first row, delete first column. So A11 determinant, this is a capital A11. Delete row 1, column 1. So only A22 remains. It is a 1 by 1 matrix. The entry is A22 minus A12. Okay, now what is capital A12? Capital A12, delete first row, delete second column. So what remains is A21. So this is a determinant of this 1 by 1 matrix. A21. So let me continue here. Okay. Determinant of a 1x1 matrix is only the entry. So it is a A11 times A22 minus A12 times A21. Done. Yeah. So a 2x2 matrix determinant, the formula is A11 times A12, A22, A11 times A22. This is the product of the main diagonal entries. A21 times A12. So this is the product of anti-diagonal entries. So determinant of a 2x2 matrix is equal to the product of the main diagonal entries minus the product of anti-diagonal entries. That is the formula to compute a 2x2 matrix. We often use this formula. I think I have to stop here. I don't have much time to present more examples. So in the next class, I present more examples about the formula to compute a determinant.